Hi everybody. Today we're going to learn about phasors. I'm Michelle Maharbis.
And I'm Vivek Subramanian. So what we're going to do today is we are going to start learning about a technique for analyzing circuits that have inductors and capacitors, among other things, in them. And we're going to use a technique called phasors to enable this analysis. Phasors are a very powerful tool, and you're going to find what they allow us to do is they allow us to take circuits that have things like inductors and capacitors and analyze them using the very simple linear circuit techniques such as KVLs and KCLs that you've already learned, hopefully, and are pretty comfortable with. So to begin, what we should do is we should figure out what phasors are. So let's go ahead and define the idea of a domain transformation. So as I've already told you, phasors are this tool that are going to allow us to use these techniques we've already learned for linear circuits. And to do that, what we do is we take circuits that have things that are responsive to alternating currents, so to AC currents, and we transform them from the standard operational domain that we work with them into the phasor domain. So what is that? Well, what a phasor analysis technique basically does is it takes our standard systems, which are time domain, I'll ask you about that in a minute, Michelle, so be warned, and transform them to the phasor domain. So, Michelle, remember the time domain stuff when we talked about currents through inductors and capacitors?
Yeah, so we had equations that related to time. So, for example, V equals L di dt.
Right. So the key point was those were differential equations, right?
That's right. And the answers we got were as a function of time. So, for example, V of t equals 3 cosine omega t.
Right.
Right. It's things that change with time.
Exactly. And so that's time domain, and now we've seen two key points. So firstly, those were things that depended on time, and they had differential equations in them, and we were solving differential equations by integrating. Well, what we get to do by doing this domain transformation, we'll introduce a concept called phasors, and the big benefit of phasors, instead of working in the time domain where we needed integral and differential equations, we now use phasors, which allows to use standard linear equations. And you'll see how that works yet. We're just introducing the advantages right now. But the big advantage is we get rid of having to solve differential equations. We'll get to use standard linear equation frameworks like KVL and KCL. And then once we're done with our analysis, we can just convert back to the time domain to get the answer that we want.
So, okay, let me see if I get it. What you're saying is that for systems that have perhaps many capacitors and many inductors, and we know that they're sinusoidal in terms of their input sources.
Correct.
We'll be able to transform these equations, which, for example, if I had many caps and many inductors, would probably be high-order differential equations. They're a pain in the butt to solve. So
exactly.
It's going to be a third order or fourth order, things we haven't even talked about in class. This will allow us to convert them into sort of a different mathematical domain, solve them easily there, and then convert them back, and that'll give us the answer we would have gotten had we done a bunch of time integration.
That's right. Now, Michelle has already pointed to a key point, which is there are going to be some caveats specifically related to what we require in terms of the voltage and current stimulus functions that we use. And you'll notice that we said here that we eliminated sinusoidal functions. We use the phasor domain in specific contexts. And Michelle, maybe you can talk about those.
The context in which we use phasors. Sure. So let's drop into that. So the context in which we teach you guys how to use phasors, or in which phasors are useful, is when we're trying to determine the steady state response of a linear circuit to an AC signal. So you see right there, there's really three conditions that are setting the stage.
I see. So I get it. So firstly, as we told you in the previous slide, we're talking about things that are time variant, but we've put a bigger context on that. We're not saying it's just time variant, but we're saying specifically it is AC.
That's right. It has to be sinusoidal. This only works with sines, which is, you're going to see all the math is sort of tricks with sines.
Got it.
The other thing is we're not solving for transients. We're only solving for what happens after a really long time.
Makes sense. And that's, so we're limiting it to AC, and we're figuring out sort of the steady state response to an AC signal.
And of course, it's got to be linear.
Got it.
Okay. So, here's an example, right, where we've got an R capacitor, an inductor, and here's another resistor, R2. And maybe what we want to do is solve for the steady state response of the voltage on this resistor.
Okay, makes sense. But now, let me try to first think about what I would have done if I didn't know about phasors. If I didn't know about phasors, I would have tried to write a set of equations that would involve the resistor. There'd be some sort of differential equation component coming from that capacitor, there'd be another differential equation component coming from that inductor, and another resistor. So I'm going to have this sort of second order differential equation here because I got two resistors, an inductor and capacitor.
That's right.
And I could solve that, and that would give me the time-dependent response that would apply in general as a function of V.
That's right, and you'd get you'd get a more general solution. You'd get transients and steady states out of that.
Got it. But now what we're going to do is we're going to limit V to a sinusoid, and that's going to simplify the way we deal with this.
That's right. If we know that Vs is a sinusoid of this form, and this is just a general form for a sine, we've cast it as using a cosine as a reference. So it's got an amplitude V0, it's got an angular frequency omega, and it's got a phase shift to that angular to the oscillation, which we call the phase angle or the phase shift phi.
Okay, let me see if I understand this. So you just chose to cast it as a cosine because that's a convention.
Yeah, it's for convenience, I could have done a sine if I wanted to.
Okay, and the omega is the frequency, and the fact that the phi is there is just to allow for a general solution. Phi could be 0, it could be some non-zero value.
Right, exactly. And the reason this will come in is as we solve things, everything will be a sinusoid, but what will change is the amplitude and the phase shift.
Got it, makes sense.
So now why is this useful? It's because sinusoid inputs are very, very common in electronic circuits. That's one. But even more powerful, and this is the thing that after we finish teaching you all this, we'll come back to in quite some detail, you can represent any time-varying periodic signal with Fourier series. And so this allows us, if I know the answer to what this circuit will do for a sinusoid of a given frequency, or I have the general answer, you can imagine I can solve it for any frequency, and all of that together, I basically can construct any periodic signal. So the response to any periodic signal.
Let me see. I think I remember this. So the idea is, if you have a square wave, you can build a square wave up as a sum of a bunch of sine waves of different frequencies.
That's right.
And that's the Fourier series concept.
Exactly. So all periodic signals can be constructed from a sum of lots and lots and lots of sinusoids.
Okay, makes sense to me.
And then the last piece of this, by the way, is we've already said, the last piece comes down to the fact that solving circuits more complex than the one we've shown on this slide would really be cumbersome, right?
To be honest, even this is pretty cumbersome.
Yeah, sure. Don't admit that. But you know, if I had another 2 caps and a third inductor, you know, it would get not crazy, but it would just be really onerous to do a time domain differential equation solution.
Right, because it's now gets to a third order or fourth order differential, which can be a real nightmare.
Right.
Okay, makes sense. So now, to do this, we've been talking about this mysterious phasor, and we haven't really told you what a phasor is yet. Now, I'm going to give you a little bit of a preview. I'm going to tell you that phasors involve using complex numbers. So to review, let's go ahead and start by just sort of reviewing what complex numbers are. And I'm going to introduce some concepts and some nomenclature that will help us when we start talking about phasors specifically. So remember first that complex numbers involve the square root of -1, and in engineering we tend to denote that as j. Okay, so j is the square root of -1. Now you'll remember then from your math classes where you learned about complex numbers that one way of denoting complex numbers is with rectangular coordinates, where we denote an arbitrary complex number z as the sum of a real component x, okay, and an imaginary component y, and so then we'll write it as z is equal to x plus jy. So if we had some arbitrary complex number located right at this point over here, we see that it has and we plotted the real on the x-axis and the imaginary on the y-axis, this number would have a real component associated with x and an imaginary component associated with y, hence z is equal to x plus jy. Now what that means is we can say that the real part of z is just x, and the imaginary part of z is just y. Now that's one way of denoting it. The other way of denoting it is the polar coordinate system. Okay, so we have the polar coordinate system, and the polar coordinate system is based on the fact that we could describe the same point over here by an angle away from the real and a length of a diagonal. Okay?
Makes sense.
And that actually comes from some basic trigonometric relationships that we know. Okay? So let's say we want to find this point here. You would agree with me that just based on standard trigonometric relationships, the length of the x-coordinate is just going to be z cosine theta.
That's right, yeah.
Okay? And then correspondingly, the length of the y side, in other words, the imaginary part, is going to be z sine theta.
That's right. I vaguely remember that.
Okay? And that comes just from straight relationships between cosines and sines. Okay? Further, we can find the length of this diagonal, as the square root of the sum of the squares.
That's right.
Okay, so here's the three relationships we have. We have x is equal to z cosine theta, y is equal to z sine theta, and z itself is going to be the square root of the sum, and more specifically the positive square root in this case, of the sum of the squares x squared plus y squared. Okay?
And you can also figure out the angle from the arctangent.
That's right. You can figure out the angle from the arctangent just based on trying to figure out this angle. You know that the opposite is y, the adjacent is x, so theta is going to be the arctan of y over x.
Okay, so basically, if you get a complex number in either form, if you get x plus jy, or you get magnitude and angle from the polar space, you can use these four equations here to just go between them.
That's right.
Switch between the two forms.
That's right. And Michelle, you pointed out something sort of interesting about the nomenclature that we use. A standard way of writing polar coordinate form is, instead of saying that z is the diagonal and the angle is theta, you'll often see us write it in this form, where we'll write z, and we'll put it between these lines to indicate that it's a magnitude, and then we'll just put the angle as this angle sign and theta. Now, notice one key thing, and that is that we will often write this in the following form. Instead of writing it as angle theta, we'll write it as ej theta, the exponent of j theta. And the reason we get to write it that way is based on a relationship that you should have seen before when you learned trig, which is the Euler's relationship. And specifically, Euler's identity states that if we have an exponential of a number that's a complex form, so in other words, e to the j theta, and it could be plus or minus j theta, that is identically equal to cosine theta plus minus j sine theta. So if this was a plus sign here, it would be cosine theta plus j sine theta. If it was a minus sign, it would be cosine theta minus j sine theta. So now think about what that means. If we take this form where we have a cosine and a sine, we can basically replace this form here, where we've got the rectangular coordinate, by a polar form, and the polar form can now be written in terms of an exponential.
Oh wow, so that's pretty clever. So basically what you're saying is, if I just by simple substitution, this expression, if I break it using this, this identity, I get magnitude z cosine theta plus or minus amplitude z, magnitude z rather, sine, j sine theta.
Right,
And
and
so-
compared to the form up there.
Oh, that's right. And so that's exactly right. That would be the x part would be magnitude z cosine theta, and the y here would be magnitude z sine theta, and that not coincidentally matches what we wrote here. So
Exactly.
it's all basically self-consistent.
Right, this is the whole point. So all I do is, if I take this exponential j theta and I replace it by the cosine and j sine that comes from Euler's
Then I
identity,
get
it's
recaptured.
exactly the same as here.
Cool. Okay, so that's a good review for complex numbers. I imagine some of you are vaguely remembering this. You're using recollection to but we'll warm you up and walk you through some of this.
Right, but we do recommend that if you're completely lost at this point, you need to go sort of review your complex math, because you do kind of need to be fairly comfortable with this to move forward.
Yeah, I agree. Okay, moving on. So now what's the actual phasor domain definition? So what we're going to do is we're going to use these concepts in the last slide, particularly that Euler identity and this notion of real and complex numbers, to play a trick. Okay, now I'm going to show you the trick. It's actually already up on the slide, and then I'm going to give you one warning I give to students in terms of sort of like dealing with it, just kind of being bothered by it. Okay, first of all, let's take an arbitrary waveform. This happens to be a voltage. So time domain voltage, this is something you could have solved for, or maybe it's your source. Again, V0 cosine omega t plus 5.
Okay, now I'm looking at this and I see you've already set it up as a sinusoid, so therefore it is a good candidate for a phasor domain analysis. And I see that it's the generic form where I have omega t in there as the angular frequency times the time, and then I have that generic phase offset built in.
So, remember this identity we just showed you, Euler's identity, right? Okay, that means that this expression is the real part of this expression.
Okay, hold up. Let me see if I understand this. It's the real part because it's only the cosine part, and the sine part has the j. So
Right.
essentially what I'm doing is I'm canceling that second part over there
Right. You're
by just
basically
taking the
ignoring
real.
that.
I'm truncating that off.
That's right. So here, and we have this V0, right? That would go in the front, so you get that. And then e to the j phi times e to the j omega t is the same thing as saying because when you multiply them, you just add the exponents. So this is e to the j omega t plus phi, which is what this is. You see?
Yep, got it.
So we're just using this identity to recognize this. Now, so far, this doesn't give us anything meaningful. It's just a little mathematical trick. It happens to be true that this is the case, okay? Now, next thing I'm going to say. You may or may not remember this, us saying this either in class or in the modules, but a linear circuit, when given an input at a particular frequency, that linear circuit may change the amplitude and it may change the phase shift, but it will not change the frequency. This is key. This is the difference between a linear and a nonlinear circuit.
Right, and let me see if I understand this. And the reason for that is a linear circuit is only responsive to what's happening at the current time, effectively, in its current situation. And if it's going to change the frequency, then it has to affect the future or the past.
Right. That's true. But think about it, another way to do this. If there aren't any exponents, so something squared or something cubed, then you're not going to get frequencies here that aren't the basic omega, right? Because if you cosine squared, you're going to start getting crazy stuff. So that's an even simpler, I think, way to look at it. But nevertheless, it's true. So if that's true, this j omega t is going to stay the same as we solve for our answer, right? If
I see. So for any circuit, that's going to be the same throughout.
For any circuit and for this given stimulus. So if I have a particular circuit and I put in a 30 hertz input, let's say this omega t is 2 pi times 30 hertz, right? I go solve and I see what the cap is doing and the currents through the cap and inductor, and I get all these answers. This part will never change. It'll always be that the answers have 30 hertz, 2 pi 30 hertz as the omega part.
Got it.
That's never going to change.
Got it.
Okay. Now you could also, by the way, you could also put in other frequencies at the input and you'll get those same frequencies at the output. You can certainly add other things by linear superposition, but it's always true that the circuit's not going to distort an input frequency to something else. So because that's true, we have learned in our notation, in our phasor notation that we are about to use, we are going to ignore this. Okay?
So we know it's there.
It's there.
We just don't write it.
We're just going to ignore it. Because what's the point of just writing all these e to the j omega t's all the time when that's not going to change? It basically, in many cases, even drop out. So here is a time domain. Here's an example. This is a time domain voltage with no phase shift. This happens to be 0. So I just get V0 cosine omega t. In the phasor domain, right, this is gone. This is 1, because that's 0.
Right.
We're ignoring this. So our phasor is going to be the thing we take the real part of. It's just going to be V0. Now this is just a notation, and it's a transform. Okay, so we're just saying we're inventing something called the phasor domain. You can think about it as another universe where we're identifying this boldface V as the phasor. The phasor is the thing we take the real part of.
I got it. And the reason, so the phi dropped out because we never had any phase shift to begin with, and the omega t is actually there, we just don't write it.
Yeah, and some people refer to the phasor as the thing you take the real part of without the e to the j omega t. That's probably the better technical definition. But nevertheless, that's what this is. Now, if I let's say I put a phase shift, the more general case. Well, now the phasor is just going to be V0 e to the j phi. So notice the phasor has a magnitude and a phase shift, and that's it.
Right.
In this case, the phase shift is 0, but it's there, right? Either the J0 is 1.
And the reason I got to do this was because if it was omega t plus phi, I could have separated that into e to the j omega t times e to the j phi, and so I just keep the j phi part and I don't write the omega t part.
That's right.
Got it.
Now, what do I find students get bothered when you do this? A couple of things. One is that this e to the j omega t goes away, and then they forget to put it back, or they're just bothered that it goes away, or why is that? How can you ignore things? Remember that we're defining our transform, and we know it's there. The second thing I find students get bothered by is like, what happened to the imaginary part? Like, what do you mean? Like, are you ignoring it? Like, why do you do stuff with this and then choose to take the real part? And that, that's the transform we've defined. It's where we're keeping we recognize that the time domain solution is the real part. We transform into the phasor domain that has, sort of both, if you want to think about it that way. We do all of our mathematical things we're going to do. We're going to do those in a minute. And then we transform back to the real part. Don't worry about the imaginary part, right, for the moment. It's just we transform back to get the real part, and that's the actual time domain change.
And if I understand, the reason for that, if I understand correctly, is, well, we're dealing with these linear circuits, so any circuit transformation on the real part should apply equally throughout. And so when we transform back, it should still work.
Yeah, that's exactly right. So that's the case. Now, so we've invented this little thing, time domain, we go to phasor domain. Now you may say, well, oh God, what's all this work for? You'll see. What's going to happen when we do this is that all of our inductors and capacitors are going to get really easy to deal with, and all of these circuits get very, very easy to solve.
So, it's worth thinking about it a little bit, and you should review this. But remember the key point. The key is to get used to this idea of going from the time domain to the phasor domain, and remember what these notations mean. Once you accept that that works really well, you'll find circuit analysis will be really easy.
And by the way, we forgot to point this out right at the end, which is that this is another way to write this thing, as we've told you before. So you may see this notation for this in the slides ahead. Okay, let's try a resistor. I think that one's pretty easy, right? So let's look at how a resistor works in the phasor domain. Oh, and we forgot another example. Okay, so this is just a little example to practice with, which is to give you something concrete. If the phase shift happened to be, say, minus pi over 2, you put the minus pi over 2 here, and now you get v0 e to the minus j pi over 2. It's just
okay, so and I bet if I were to write that in this sort of notation, I would write v0 and then angle sine minus pi over 2?
Yeah, that's it.
Okay, makes sense to me.
All right, easy enough. All right, let's move on.
Okay, so now we'll move on, and we will talk about a resistor. Okay, and I picked the easy one. Michelle's going to get the harder one. All right, I'm going to work with the resistor. So first, let's just do this intuitively. Michelle, if I were to apply an AC signal to a resistor, do you expect the voltage and current to be different in terms of phase? Just I take a single resistor and I apply an AC voltage to it.
No, because if I let's say I put 1 volt times cosine omega t plus phi, and I go it through a resistor. Let's say that's the current, and I run it through a resistor. Well, the voltage is just going to be that resistor, which is a real number, times the current, and I get back the same thing, except I multiplied the amplitude by something.
Exactly right. Okay, so let's go ahead and see what that really means in the time domain. Let's say I have a current that I'm imposing on a resistor, and the current is some magnitude Im, and we're going to do it with a sinusoid, so we'll say it's Im cosine omega t plus phi. And I've taken this generic form so that it allows for an arbitrary phase shift. Well, Ohm's law says V is equal to IR. Okay? And Ohm's law is not limited to the DC case. It applies equally well in this AC case. So we're just going to take this current and we're going to multiply it by R. So we get the voltage is equal to R times I, which is R times Im cosine omega t plus phi. Woohoo! Okay, so that's time domain. Makes sense? Now, let's see how we would do it in the phasor domain. Well, remember my phasor domain notation. How would I represent I, Michelle, in the phasor domain?
Well, so in the phasor domain, it's Im, which is the magnitude,
right.
And then you would have like a little angle sign and have the phi, or you could say it's e to the j phi.
Okay.
Anyway. So the phasor would be Im magnitude, and phi would be the phase shift of the phasor.
I agree. So you agree. So now we'll use the sort of bolded notations to indicate the phasor domain. I should add, that's not universal. You'll find some texts that don't use the bolded notation.
No, so, and some even use these little double bar letters.
That's right.
Yeah.
Okay. So, but we'll say V is equal to IR, or V is equal to RI, same thing. And now, as Michelle said, I in the phasor domain is Im angle phi. The angle indicates that that's the phase, and the omega t we don't have to show based on our standard phasor domain nomenclature. So you see V is equal to Ri, and that's just going to be R, Im, angle phi.
Okay.
So you saw the beauty of this. Now, the resistor is a trivial case, because resistors are easy to deal with even in the time domain, but I could use the same tools that I had. I used Ohm's law, and I used it in the phasor domain just as I used it in the time domain.
Okay, so in a phasor domain, R looks like R.
Exactly.
Okay, that doesn't mean a lot to you out there if you haven't seen this before, but you're about to see the next case how we transform something else. It's a little more complicated. Okay, let's do an inductor. So current through an inductor, we're going to take the same tack. We're going to know the current. We're going to say the current is Im cosine omega t plus phi. Now, how are current and voltage related in the time domain for an inductor relay?
Okay, well, for an inductor, I know that the voltage is L times di dt.
Okay, now we know that's true for the time domain. This
Right.
expression is true in the time domain. I'm going to come back to that in a minute because this is a typical error people make when dealing with this. So, okay, this is true in the time domain. Fine. Now, in the phasor domain, we know that the time domain voltage is the real part of our phasor and this e to the j omega t business that we tend to ignore most of the time. So remember, this is the phasor, this VL thing, right? And the IL thing.
So you haven't told me what that phasor is right now. You're just saying if I have a phasor VL, the voltage will just be VL is the real part of VL e to the j omega t.
Exactly. I'm just remembering, basically it's just remembering what we told you before. Now, as an example, the same example you made me do in the last slide, for this current here, this would be, this IL, the thing you're taking the real part of, this IL would be Im phi, e to the j phi, e to the j omega t, multiplied over here.
Okay, let me see if I can review that. So what I've got is IL,
Yeah.
and IL is Im angle phi.
Yeah, or
right?
e to the j phi.
Or e to the j phi, and I've got that multiplied by e to the j omega t. So that is e to the j omega t plus phi, and the real part of that is just going to be the cosine.
Yeah.
And so that gives me back
And that
this
gives you
form.
back that.
Got it.
Those of you that are doing this again, we're kind of beating this to death because we want you to go through the paces of kind of thinking it over and over, doing it on a piece of paper. Okay. Now, guess what we're going to do next? Well, we know the relationship between the current and the voltage in the time domain. We know what the voltage in the time domain looks like as a function of the phasor. We're going to substitute in. So in other words, V, time domain V, this whole thing is time domain V equals L di dt, where this is the I. See?
Right, I got it. So you just took that top differential form, V is equal to L di dt. For V, you plugged in this one, and then for I, you plugged in that one, and so now we have to take the derivative of that.
Now, is there anything just in this capital IL that depends on time?
Yeah, it's the exponential form. Oh, you mean just in the capital IL?
Just in the capital IL.
Well, let's see. We've separated out the ej omega t, so I guess the answer is no. I should be able to just bring that out.
That's right. This IL just has the magnitude and the phase, right? We pop this out, that's why it's here. So is there a time derivative of this? No.
No, that just pops out of the equation.
Exactly. That's
Okay.
going to come out. And what's left is e to the j omega t. What's the derivative of e to the j omega t?
Oh, that's easy. The derivative of an exponential with a prefactor is just going to be the prefactor times the exponential itself.
Right,
So,
so
it's going to be j omega times e to the j omega t.
Magic. See? So now what happened, this time derivative in the time domain, in the phasor domain just becomes a j omega.
Got it.
So now, what's the beauty of this? The phasor voltage is equal to j omega L times the phasor current only in the phasor domain, or the frequency domain, however you want to think about it. Okay? So look, now here's the trick. In our time domain, this was a real pain in the butt because every time we wanted to link I and V for an inductor, we got this derivative. In the phasor domain, it's almost like a resistor. It's just you're multiplying the I times this thing that depends on L to get the V.
Huh, that's weird. So I've gotten rid of my differential equation. I now have an equation that's a linear equation.
Yeah.
I mean, it's got complex numbers in it, but it's still a linear equation. It's easy to deal with. But that thing you pointed to, I mean, j and omega, so j is j, omega is in angular frequency, and you got L in there.
Well,
But that has a relationship kind of like Ohm's law, except instead of having R in there, it's got j omega L.
right. So it's just like Ohm's law, except it's purely imaginary, right? And it's dependent on the frequency of the input. And we call this, not we call this, but I guess it allows us to start thinking about a concept we call impedance, which is actually sort of the general parent of resistance. It's the general form. So if I take a phasor V and divide by a phasor I, for an inductor, and only for an inductor, I get this expression, j omega L. So we can think of this almost like resistance, but it's called impedance. We're going to come back to this in great detail because impedance will have both real and imaginary components, and the R's will always be the real parts, and the capacitors and inductors will always be imaginary parts. But we'll get to that. We'll get to that in a minute.
Well, maybe I can do another example. Maybe we can do on capacitors.
Why don't you do the cap?
All right. So capacitors will be a little easier since Michelle's already done the hard work and set up the inductors.
That's right.
All right. So remember, we're going to use this. Now we're going to use a voltage stimulus, okay? Because we're going to use a cosine omega t plus phi multiplied by Vm for the voltage, and we're going to try to figure out the current, okay? And now in a capacitor, you know that the current is just equal to C dV dt. All right, so that's from your time domain analysis. So in the time domain, what you would have is I is equal to C dV dt. In the phasor domain, using the same analogous framework, remember what we did when we took a derivative in the phasor domain, we just wrote that as j omega. So what happens is now when we write the phasor domain relationship for a capacitor, where we had I is equal to C dV dt, we write IC, the current through a capacitor in the phasor domain, is equal to j omega C times the voltage V of C. And so this is the phasor domain relationship for a capacitor relating the current to the voltage, and then we can correspondingly write the impedance for a capacitor as the voltage divided by the current. Because the capacitor relationship is C dV dt as opposed to the inductor, which was what, Michelle?
L di dt equals
Right.
V.
Okay, so now here, because of that, when we do the V over I, the j omega goes into the denominator, and we get the impedance of a capacitor is equal to 1 of j omega c.
Right. So remember, in the inductor case, we had V equals j omega Li.
Right, and here we have I is equal to j omega CV, and so the impedance is going to be the reciprocal form.
Exactly. Okay, so what do we know? We know that an inductor in the frequency domain looks like, has an impedance of j omega L, and a capacitor in the frequency domain has an impedance of 1 over j omega C. All right, and a resistor has an impedance of?
Same thing as its ohmic value, so it's just R.
Just R. That's resistors are trivial. All right. So now let's go through a general analysis of how we're going to use this to solve circuits. So we've walked you through, how an R, an L, and a C look in the phasor domain. Now we've got to give you an actual method, right? This is like when we were teaching you KVL and KCL. So here's the method. And this is what you follow at the beginning, just sort of almost, I would say, blindly until you get a kind of intuition about it. Step 1, turn every input, every source that you're given, into a cosine referenced sinusoid. By that I mean turn all the sines to cosines.
So we'll just do the phase shift to achieve that, basically.
Yeah. So let's do an example. So let's say here I have a circuit. It's an RC circuit. We've done these before. In the time domain, we have an unknown current I.
So you want to find the current.
Yeah, we're gonna in a minute we're gonna solve for this current I,
Okay.
and we're told the source Vs in the time domain looks like 12 sine omega t minus 45 degrees. Okay.
Got it.
Now we don't want to keep it in a sine because otherwise, if we don't flip it to cosine, we're going to get a bunch of 90-degree phase shift errors. Why are we doing cosine? Just because, right? Because we have to pick one or the other.
Right, and that's sort of become the standard that everybody uses. People tend to do things in terms of cosines.
Sure. Some people like the fact that the cosine has a particular symmetry with the y-axis, but that's all that's all sort of second order stuff. So anyway, when we convert to cosine, we're going to get 12 cosine omega t plus 135 degrees, right? Because we have to shift by 90 to get to here. Okay, so here we go. I'm shifting to cosine reference, and there it is. Actually, this is the phasor. I'm jumping ahead. The exact would be what I said, 12 cosine omega t plus 135. Okay, so step 2. Step 2 is I transform my circuit from the time domain to the phasor domain. Now here's where a lot of people make mistakes. Why do they make mistakes? Because these two circuits look kind of the same, right? The topology is certainly never changed, right? The connection diagram doesn't change. But the components have to all be transformed, all of them. And sometimes people will do one and not the other. So they'll keep like, the worst offenders will keep here on they'll keep a Vs of t on the voltage source, and then they'll transform the components to the phasor domain, or maybe they'll leave this as a real capacitor and they'll transform this. I don't know, but basically do it all. So teach yourself to go component by component and change all of the values to phasor, and all of your variables that you're solving for must be phasor variables. They can't be these little time domain i's. They have to be this, okay? So let's do that. What's the source? The source is going to be what's the phasor that corresponds to this? It's 12 and 135 degree phase shift, right? Because the omega t is ignored, right? So 12, 135.
And the 135 is just because you had the change from the sine to the cosine.
That's right.
Okay.
R, okay, here's our little lookup table. R just goes to R. So that's fine. We just put R. We've just 3
Haha,
R's.
you learned something from me, Michelle.
I've learned many things from you, Vic. Okay, and the C goes to 1 over j omega c. You just put that in there. That's the impedance of this device in the phasor domain. Okay, so far so good. We haven't had to do anything really difficult.
All right, so now let's go ahead and maybe try to perform an analysis on this. So, well, Michelle, I look at this. How would I normally solve this circuit?
Well, so this is the part we haven't really talked about. If I had to do this circuit, I would maybe write a KVL equation, right? I'd start at the bottom left corner and say minus Vs plus the voltage drop across the resistor plus the voltage drop across the capacitor equals 0.
That's right. And now, here's the beauty of it. We know how to do this. And the reason we know how to do this is remember, this resistor has a value R, and we call this the impedance. And the impedance is the relationship from the voltage to the current, right?
Oh, so we can do the same trick. Now, hold on, though. Does that mean that KVL and KCL all hold in the phasor domain?
Yeah, we can still do KVLs and KCLs in the phasor domain,
That's awesome.
provided we keep our frameworks correctly set up. So you set it up for cosine references, you live there, you make sure everything is set up in the phasor domain, and then you can go back, okay? So we cast the equation in the phasor form. So basically what we want to do is we want to find I through the system. Well, the KVL tells us, since I is continuous throughout the system, it's going to be I times the total impedance plus resistance, you know, seen across the system is equal to V. So we got I. Remember, these two are in series, right?
Yeah, this is my KVL equation, right?
That is your KVL equation.
Vs plus IR plus I times 1 over j.
That's right.
Cool.
And that works because these are in series with each other and they're the same current going through them. And we treat, for the purposes of our phasor analysis, these impedances that we have, we treat them exactly like resistances in terms of how we deal with them in KVLs and KCLs.
Sure.
So we get I times R plus 1 over j omega c is equal to Vs. Okay?
It's pretty easy.
Yeah, that is. Now we can solve for I because this is a linear equation. Right? So we can just use all our linear equation tricks, and this is a trivial
We can use our deep knowledge of mathematics to take the thing on the left and put it on the, on the right.
That's right. But remember, this is an easy case. But let's say we had simultaneous equations. We could still solve them in this linear form, which is great, right? And so we can solve, and now we find I. Now, let's go ahead and take the actual step then of going back from this form. This is all in the phasor domain. Let's figure out how we would go back into the time domain.
Oh, that's right. We've got to go back because the thing I want is the time domain current.
Right.
That's the real quote-unquote answer.
Exactly. Now,
No
here's
pun
the
intended.
right. But here's the key point. Here's what we're going to do is, for example, if we had our problem set up, and you know, on the previous page we had some numbers set up for it. Well, when we solve the problem, let's say we have the real part of this problem, and it's I e to the j omega t, and we want to take the real part off it. What we're going to do is we will essentially go back by essentially plugging in our j omega t. We take the phase shift that we had, we put that back in. We take the magnitude that we calculated, we put that in, and what we end up with is a cosine form.
Okay, what you're saying is, you know, we invented some numbers, but you're saying, you know, when we solved for the phasor I here, the answer we got just by looking at this must have been 6 phase shift of 105.
Phase shift of minus 105.
Minus 105.
Correct.
Sorry, minus 105.
Right.
And so then when I took the real part of 6 e to the j minus 105 e to the j omega t, the real part of that is obviously 6 cosine omega t minus 105.
And you notice what you did. You did two things. One is we kept track of that phase shift and we propagated it through. And then to go back to the time domain, we plugged in that j omega t that we've sort of been hiding.
Brilliant. All right, that works for me.
And that's it. That's the
method.
basic idea. So maybe we can do, Michelle, since you were mocking my solution of a relatively simple problem, maybe you can do one.
I was not mocking you, sir. All right. So here's another one. This is a circuit with an inductor. So you have
and this is going to be so much harder in terms of the KVLs, Michelle.
I didn't claim it was going to be any harder. I hope it's easier. So, so this is the source, and the resistor and the inductor, and going to solve for the voltage across the inductor.
Okay, go for it.
I think that's what we're going to solve for. Let's find out. So we're told the source is 15 sine 4 times 10 to the 4th. That's our omega. They're just given to us. T minus 30 degrees. So what do we got to do first?
All right, well, let's see. We know what the omega is, and we know what the phase shift is, so it seems like we should set up a phasor domain system to describe this voltage, but this is in a sinusoid form, so we probably need to go to a cosine form.
Bingo. So we've got our cosine reference this thing. That's always our step one. So we've got a phase shift of 30 degrees. This obviously doesn't change. We just got to shift by minus 90. So now it's 15 cosine, the same omega, minus 120.
Got it. So we just added the 90-degree phase shift to the 30 that we had.
All right. As a preview, Vivek, what's the phasor for this source? Since we're about to do that, right?
Two parts. First, I sort of pull that omega t out so I don't have to keep track of that. And all I got to do is keep the phase shift. So it's going to be 15 angle minus 120.
That's right. Look at that. Look at that. All right. Perfect. So now we've phasor transformed the source sort of ahead of time, right? Just because we can. Now we're going to transform the whole circuit to the phasor domain. So that Vs we've just done. R is just going to go to R. This is going to go to j omega L. Now, we can keep it in symbolic form for now, but if we need a number, we could do it right away, right? Because we've got J.
Right.
What's omega?
We know what omega is. It's 4 times 10 to the 4.
Oh, that's right. There it is. And then L is somewhere up here. 0.1 millihenry. So we could multiply all that stuff together. We'd actually have an omega L, an actual number. And J, of course, is always J. It's the square root of minus 1. Okay. So we've transformed our circuit. You've noticed that the currents and voltages have been cast in their phasor symbols. I know this is sort of nitpicky, but it's important. We just teach you good discipline, not to make a mess. And now we've got to solve for the corresponding phasor of the thing we want. So we're going to solve for the phasor for VL. Now what we're going to do first is we're going to solve for I. All right?
Okay.
So we pretty much following what we did with you in the last example. Ri plus j omega L times I equals Vs, right? This is doing KVL around the loop. There it is. We're going to start by solving for I, right? This is one way to do it, right? You could do it a number of ways, including an impedance divider, but for the moment, let's just solve for I. So factor out I, you get I times R plus j omega equals Vs. Divide by that. There you go. Look at that deep math again. I equals Vs over R plus j omega L. Now we've got all these numbers. So this is the source. We had already transformed this.
Okay.
Now,
and then R is 3 ohms.
Uh-huh.
And then j omega L is J, and the omega was 4 times 10 to the 4, and the L was 1 millihenry, which is 10 to the minus 4 henries.
Wait, 1 millihenry is 10 to the minus 3. Was it 0.1 millihenry?
Oh, it was 0.1 millihenries.
That's
You're
right.
right. Yeah, correct.
Yeah,
It was 0.1. Yep.
So okay, so we keep this at the top this way, and then all this gobbledygook, we compress it. We take all the real numbers and put them in, on one side and all. Now, of course, these two things go to 1, right? Just by convenience. And so you get 3 plus j4. Now here, Vivek, what would you do?
Well, so the problem I have is, the problem I have is the top is in the polar notation and the bottom is in the rectangular notation. So I have two choices. I could go everything rectangular, everything polar. It's often easier to do multiplication and division in polar form just because the angles just subtract out.
Exactly.
So what I'd probably do is convert that bottom to the polar form. So that's easy to do. To find the magnitude, it's the square root of 3 squared plus 4 squared, which I know is 5. And to find the angle, I just take the arctan calculated from the real and imaginary parts, and that happens to be 53.1 degrees.
Right. And then it's easy because the magnitude's 15 over 5 is 3, and then these actually, when you're dividing, you subtract, right?
Right, so it's minus 120 minus 53.1, so it's minus 173.1.
If you were multiplying, these would add, and these would multiply. So
Got it.
That's easy. So our phasor, now here's the trick. Our phasor current I is 3 e to the minus j 173. In other words, it's got a magnitude of 3 and an angle of 173. But the key now is, what do we do with that? Well, we wanted to solve for this VL. So how do you think before I move on, how do you think we're doing?
Well, given that you told me that I can still use all my old linear circuit analysis tricks, I'm just going to multiply I by the impedance, and that'll give me the voltage.
That's right. So I, j omega L, should give me VL.
Got it.
There you go. So VL is going to be j omega Li. We just solved for I. Right? That's this business. And remember, omega L, so this is omega, and this is L, so these will cancel out again.
Okay.
And we'll get 12, J12 e to the minus J 173. But there's a J here. What are we going to do now?
Well, so the difficulty here that I have is I have the J, but I also have my polar coordinate representation of the rest. Well, I do know one thing that's kind of useful for us. I know that J I can represent in polar form as well by taking advantage of the fact that J can just be represented as E to the J 90 degrees. Now think about why that's true, okay? 90 degrees is shifting us purely imaginary.
That's right.
Right?
So I guess, that's right. Sine of 90 degrees would be 1, right?
Right. So it's shifting us to the vertical axis. So essentially, by taking advantage of the fact that I'm shifting the pure imaginary form, when I do that, J can be written in the phasor space as E to the J 90.
Oh, I see. Yeah, because by Euler's, this would be cosine of 90 plus j sine of 90. Cosine of 90 is 0, j sine is 1, so you get j.
Exactly.
Perfect. Okay, so why did we do this trick, by the way? Because we're thinking ahead. We're going to take the real part of this, and we know we don't want to take the real part of a j here. So here's an interesting little detail, though. Basically, what we're saying is, if you've got a j in your magnitude, it's equivalent to just phase shifting this by 90 degrees. Because what are we going to do, right? These two things are multiplied. That means this is just going to be minus 173 plus 90.
Right.
So we just shifted the phase shift by 90. It's a little detail. For the moment, most of you probably don't intuitively see that, but as you work with this more, it'll become useful. So, but now we have a nice expression for V.
Though hopefully the mathematics of it makes sense to you. I mean, because that's pretty straightforward.
Yeah, exactly. So at least get to the point where you follow what we're doing. But now that we've got this phasor V, what do we got to do?
Well, let's see. I can plug in the values I know. I can go ahead and get back to the time domain if I want, because now I know the omegas and I know the inductances.
That's right. Let's do this. So first we've got to, do this little phase shift, and now we're going to transform to the time domain.
Okay.
So the real part.
All right, so that's easy enough. I take the real part. I put multiply by j omega t first to get that back into the equation.
And that's another common error. People always forget to put this back. So they take just the real part of this thing, right? And they forget that they've got to do e to the j omega t. So we're telling you like 3 times now, I think, in this module we've told you this.
Right. So we put that back in. We sort of take the real part, which means we're just keeping we combine those exponentials. We keep the cosine only, and we're done. So we've got 12 times cosine 4 times 10 to the 4t. That comes from the omega part. And then we got the 83.1 degree phase shift.
Right. Now, had you done this all with differential equations, you would have gotten this answer, but it probably would have taken you a lot longer.
Right, and both of the cases we've looked at here have been pretty simple. In the time domain, they would have been relatively straightforward as well, because they are first order differential equations.
Oh, that's true. We were doing first orders.
But you can see the advantage of this. We can have really complex circuits and do KVLs and KCLs and superposition and all those techniques that we've learned we can apply now. And just as long as we learn this phasor transform back and forth, life is easy.
Yep. So what we're going to do in the next module is we're going to expand this and just kind of touch on topics you've already seen in the context of resistors only, and just show you how they work in the phasor domain. It's pretty straightforward. And then we'll do a few more examples to kind of round out this section. But what the beauty of this is we will be coming back eventually and showing you how this leads to all sorts of intuition about filters and about all, really this is the beginning of a really wonderful path into understanding how a lot of linear circuit stuff works.
Sounds good.
See you soon.